Hello everyone, welcome to Soft Science. Tonight we'll talk about something that sounds simple but stretches the boundaries of space, physics, and our understanding of the cosmos. The coldest places in the universe. Let's start with a question to drift on. If you could fall asleep on any planet, which one would you choose? It's a cozy thought, imagining yourself curled up on some faraway world, the stars glittering above you. But not all places in the universe would make good resting spots. Some are unimaginably cold, colder than any winter night on Earth, colder than liquid nitrogen, colder even than outer space itself. And that's where we're going tonight. So tuck in, relax, and let your mind float outward. We're going far beyond Earth, beyond warmth, beyond light, into the most frozen corners of reality. Let's begin with something familiar: space. Even in the vast emptiness between stars, space is not truly empty. There are stray atoms, radiation, faint glimmers of starlight travelling endlessly. But it is cold, so cold. The average temperature of space, far from any galaxy or star, is about 2.7 Kelvin. That's just 2.7 degrees above absolute zero. Absolute zero Kelvin is the point at which all atomic motion ceases. It's a theoretical lower limit. Nothing in the known universe should be able to reach it, yet some things come astonishingly close. This average temperature comes from something called the cosmic microwave background, the lingering afterglow of the Big Bang. It's everywhere. It bathes the entire universe in a nearly uniform cold. When you're not near a star or a planet, this is the ambient temperature you'd find 2.7 Kelvin or 454.8 degrees Fahrenheit. But that's not even the coldest place. In fact, the coldest known place in the universe is a small, artificial one. It exists right here on Earth. At the Massachusetts Institute of Technology, scientists have used laser cooling to bring atoms in a vacuum chamber down to just 500 picokelvins, half a billionth of a Kelvin above absolute zero. That's the coldest temperature ever achieved by humans. It's not a place you can go to exactly, but it shows just how close we can come to stopping time, freezing movement, silencing the jitter of particles. But outside of labs, the universe itself has its own icy realms. Let's move now into deep space, thousands of light years away, to a dark cloud known as the Boomerang Nebula. This strange, hourglass-shaped cloud of gas and dust is about 5,000 light years from Earth in the constellation Centaurus. It was formed when a dying star, near the end of its life, began ejecting its outer layers into space. What makes the Boomerang Nebula remarkable is its temperature, just 1 Kelvin. That's colder than the background radiation of the universe itself. How can it be so cold? It comes down to expansion. As the gas is ejected outward from the dying star, it expands incredibly fast, faster than any other known object of its kind. And just like air from a can of compressed air feels cold when released, the rapidly expanding gas in the Boomerang Nebula cools dramatically as it spreads out into space. This makes the Boomerang Nebula not just a beautiful and eerie sight, but the coldest naturally occurring place we've ever found. Imagine floating through that region. You wouldn't see much. It's pitch black to the human eye. A telescope with special filters can detect its faint blue glow, but it's surrounded by cold vacuum and drifting molecular gas. The silence, the stillness, and the chill would be absolute. And yet, the Boomerang Nebula is only one example. The universe is dotted with similar regions, cold clouds of dust and gas called molecular clouds. These clouds are the raw material for star formation, and inside them, temperatures can drop to just 10 Kelvin. They're cold because they're dense, thick with dust that blocks out starlight, and they're shielded from the warmth of surrounding stars. You might not expect that the birthplaces of stars could be so cold, but it's precisely that chill that allows gravity to begin its slow work, pulling particles together, forming clumps that will one day ignite and shine. But let's go colder still. In the constellation Taurus lies the dark nebula Barnard 68, a thick molecular cloud that appears as a dark smudge blotting out the stars behind it. Inside, it's quiet, still, and frigid. Light cannot penetrate it. For hundreds of thousands of years, it may remain this way, a suspended breath in the life of a galaxy, until one day the balance tips and a new star is born from the cold. We often think of the universe as a fiery place, of stars blazing, galaxies spinning, black holes devouring matter. But in truth, most of space is cold. Very cold. Life is drawn to warmth, but the cosmos favours emptiness. The further you travel from a star, the faster the temperature drops. Let's explore that idea by visiting some of the moons and planets on the edge of our solar system. Take Triton, Neptune's largest moon. It's a frigid world covered in nitrogen ice and volcanic plains. Temperatures on Triton hover around 38 Kelvin, or 391 degrees Fahrenheit. It's so cold that nitrogen, which is a gas here on Earth, freezes into solid sheets across the surface. The atmosphere is whisper thin. Occasionally, geysers erupt, dark plumes of nitrogen gas shooting miles into the sky, triggered by sunlight warming the surface just enough to cause pockets of gas to burst free. Next, there's Pluto, which orbits even farther out. Though it's no longer officially classified as a planet, it holds its own in the realm of cold. Temperatures on Pluto average around 33 Kelvin. Like Triton, its surface is covered in frozen nitrogen, methane, and carbon monoxide. In 2015, when NASA's New Horizons spacecraft flew past, it revealed towering ice mountains, plains of frozen nitrogen, and even hints of a thin, layered atmosphere. The coldest known object in our solar system, though, might be the moon of Uranus called Mimas. It's a small cratered world, and certain parts of it receive so little sunlight that temperatures can drop below 25 Kelvin. But even these worlds, as remote and frozen as they are practically tropical compared to what lies farther out, in the depths between the stars. Let's return to that vast, empty space. The voids. Cosmic voids are regions of the universe where there are few, if any, galaxies. They can stretch across hundreds of millions of light years. Here, the average temperature is only that of the cosmic microwave background, 2.7 Kelvin. There's almost no matter, no stars, no planets, just a haunting silence, and the occasional lonely photon moving endlessly through space. And yet, even in these voids, nature finds ways to go colder. In the centers of certain interstellar clouds, shielded from all radiation, temperatures may dip below 2 Kelvin. These are the coldest natural environments known, and within them, some of the slowest chemistry in the universe occurs. Hydrogen molecules cling together, move sluggishly, sometimes barely reacting over millions of years. The cold slows time, not in a relativistic way, but in the way molecules behave, in the way reactions stall and fade. Cold doesn't just mean temperature, it means stillness. It means entropy reaching its lowest point. It means time itself seems to pause. Let's take one final detour for tonight, the concept of Bose-Einstein condensates. These are not locations in the universe, but states of matter, created in labs by cooling atoms to near absolute zero. At this point, atoms begin to behave not like individual particles, but like one unified wave. It's a glimpse into a quantum state of perfect stillness. These condensates are the coldest things we've ever made. They exist for moments, in vacuum chambers, under extreme precision, but they show us what nature looks like when almost all motion stops. It's astonishing to think about. All around us, atoms vibrate, molecules spin. But in the coldest places in the universe, that dance slows almost to a halt. Tonight, we've wandered from the edges of our solar system into the most frozen corners of space. From Pluto to the Boomerang Nebula, from icy moons to cosmic voids, we've seen that cold is not just absence, it's a force in itself. It shapes stars, preserves time, and reveals the quietest truths of the cosmos. And as you drift into sleep, think about the silence of those places. The stillness, the quiet hum of the universe settling into calm. Somewhere out there, in the dark between the galaxies, it is colder than anything you'll ever feel. And somehow, that too is beautiful. As we leave behind the icy plains of Pluto and the ghostly clouds of the Boomerang Nebula, we begin to understand that cold is not just a temperature, it's a condition of being. It shapes the universe as surely as gravity or light. But what happens when we look closer, not just at known celestial objects, but at the strange physics of low-temperature environments? What happens when matter itself starts to change? Let's return to Earth for a brief moment, not to the surface, but to the technology we've built to reach the limits of cold. In the deepest cold ever achieved by humans, atoms slow to a crawl. In cryogenic physics labs, scientists routinely cool systems to below 1 Kelvin. But what does this do to matter? It starts behaving strangely. At extremely low temperatures, familiar elements like helium no longer act like ordinary substances. For example, helium-4 becomes a superfluid below 2.14 Kelvin. This means it can flow without friction. Place it in a container and it will climb up the walls and spill over the edge, defying gravity and logic. Superfluids show us that cold is not just lack of heat, it's an entrance into a new phase of matter. But superfluidity isn't just a laboratory curiosity. It might exist in the universe itself, in places we can't directly reach, but can only infer. One of the best candidates? Neutron stars. Neutron stars are the ultra-dense remnants of supernova explosions. Imagine something the size of a city, yet with more mass than the Sun. The gravity is so strong it crushes atoms. Electrons and protons merge into neutrons, forming one of the densest materials in existence. But deep within some neutron stars, scientists believe that neutrons form a superfluid core, a place where quantum effects govern not just atoms, but entire star-sized structures. And these superfluid cores are cold. Not in the sense of frozen ice, but in the deep thermodynamic sense, measured in millions of Kelvin, but still considered cold in stellar terms due to the internal energy state and the lack of heat exchange. Now let's move out again, this time toward rogue planets. Rogue planets are worlds that don't orbit a star. They drift alone through the galaxy, lost or never bound. Without the warmth of a sun, their surfaces are unimaginably cold, frozen solid and shrouded in darkness. It's estimated that there may be more rogue planets in the galaxy than stars. Imagine standing on one. The sky is black, no dawn, no twilight, just the faint, eternal glow of distant galaxies. Your breath would freeze instantly. The ground beneath your feet would be harder than granite, a crust of frozen gases and rock. At temperatures possibly dipping below 30 Kelvin, time feels like it has stopped. There is no wind, no weather, no life, just cold. And yet, perhaps not entirely lifeless. Some researchers speculate that subsurface oceans, kept liquid by residual heat and pressure, could exist even on rogue planets. If so, then cold does not always mean dead, it may merely be dormant. Let's shift again, this time to distant exoplanets. Thanks to telescopes like Kepler and TESS, we've identified thousands of planets outside our solar system. Some of these orbit far from their stars, in the freezing reaches of their systems. Gas giants similar to Neptune, but colder. Icy super-Earths cloaked in frozen hydrogen and methane. The coldest of these may orbit red dwarfs or brown dwarfs, cool stars that emit little light. Brown dwarfs, in particular, blur the line between stars and planets. They're massive enough to ignite some fusion, but not enough to become true stars. The coldest brown dwarf ever discovered is WISE 0855 0714, just 7.2 light-years from Earth. Its estimated temperature, between 225 and 260 Kelvin, colder than most Earth deserts, and possibly cold enough to allow for water clouds. That's right, water clouds on a failed star. It's another reminder that cold isn't a flaw in the universe. It's part of the design. Cold is what allows molecules to condense, to organize, to slow down and combine. In fact, some of the most complex chemistry in space takes place not in hot stars, but on the surfaces of cold interstellar dust grains. Out in these frigid molecular clouds, places like the Taurus molecular cloud or the Perseus complex, dust grains float in near vacuum, coated in frozen carbon monoxide, water, ammonia, and methane. Over time, radiation and cosmic rays trigger reactions, forming complex organic molecules. Some of the very same molecules found in living cells. Amino acids, alcohols, simple sugars. In the cold, life's ingredients come together. That's the strange paradox of the universe. Heat destroys, cold preserves. Heat burns, fuses, and erases structure. Cold shelters it, keeps it from decay. The oldest meteorites, the best preserved molecules, and the slowest evolutionary reactions all favor the quiet of cold. Let's now consider cold from the perspective of time itself. In warm environments, atoms move fast, collisions happen quickly, reactions complete in milliseconds. But in ultra-cold space, reactions that might take seconds in a lab could take thousands of years. A hydrogen atom might wander for a millennium before encountering another. In the coldest parts of interstellar space, time stretches, not because of relativity, but because everything slows. Processes that are too fast to observe on Earth unfold gently over cosmic time. This brings us to the concept of thermal death. The idea that as the universe continues to expand and stars burn out and matter spreads thin, it will eventually reach a state of maximum entropy, a cold, dark, still state. Heat will dissipate, motion will cease, and the entire universe will become cold. Not the cold of Pluto, not the cold of Triton, but the cold of equilibrium, a flat, even, empty chill. No gradients, no energy, just the end of time. This is known as heat death, not because of excess heat, but because everything that could have generated warmth is gone. What remains is the faint, ghostly hum of the cosmic microwave background, redshifting into silence as the last photons stretch across the void. But don't worry, that's trillions upon trillions of years away. In the meantime, the universe is still brimming with energy, motion, and mystery. And some of that mystery lies frozen in the dark. Let's pause here and reflect on this idea. The coldest places in the universe are not simply where the thermometer reads the lowest. They are where time slows, where chemistry becomes patient, where matter reveals its hidden quantum patterns. They are not barren, they are profound. We visited icy moons and dark nebulae, rogue planets and cosmic voids. We've watched helium become a superfluid and considered a future where all things go cold. And yet, the beauty in this cold is quiet. It's not a scream like a supernova or a blaze like a star. It's a hush, a preservation, a deep stillness that says, this too is part of the story. When you close your eyes and imagine the coldest place in the universe, you might picture a blank, empty nothing. But now you know, it's not empty. It's not dead. It's simply slow. And in that slowness, the universe writes its most delicate poetry. As we continue our journey into the coldest corners of the cosmos, we arrive at a strange paradox. Even stars, the very symbols of heat and energy, can become cold. But first, let's revisit the idea of stars themselves. Stars are hot because of nuclear fusion, hydrogen atoms colliding and fusing into helium, releasing enormous energy in the process. But what happens when a star runs out of fuel? That's when it begins to die. For small to medium-sized stars like our Sun, the end comes quietly. They expand into red giants, shed their outer layers, and leave behind a white dwarf, a dense, glowing ember the size of Earth, slowly cooling over billions of years. White dwarfs are still hot when they form, tens of thousands of Kelvin, but over time, they radiate their remaining heat into space. Eventually, a white dwarf will cool so completely that it no longer emits visible light. It becomes a black dwarf. Black dwarfs are theoretical. None exist yet, because the universe isn't old enough for any white dwarf to have cooled that far. But given enough time, on the order of a quadrillion years, white dwarfs will fade into cold, invisible cinders. Their temperatures may drop to just a few kelvins above absolute zero. Imagine that, a former star, cold and dark, adrift in space, no longer shining, just a whisper of what once was. And yet even colder realms await us beyond these stellar remnants. Let's drift now into the space between galaxies, intergalactic space. Most people imagine space as being the space between stars, but that's only part of it. Galaxies themselves are clustered, and between these clusters are vast, empty regions. These cosmic voids can be hundreds of millions of light years across, containing only a few atoms per cubic meter. There's no warmth from stars, no light, and almost no matter. In these voids, the temperature is dictated by the cosmic microwave background, 2.7 Kelvin. But in dense clouds, hidden from even that faint radiation, temperatures might dip even lower. These vast, dark zones are among the loneliest, most isolated places imaginable. The atoms that do exist here have no nearby gravity wells to attract them, no stars to orbit, no planets to land on. They simply drift. And because they are so sparsely distributed, they can travel for eons without colliding with another atom. In this sense, time and space feel stretched. A single moment could last 1,000 years. A journey could span 1 billion without encountering anything at all. Now consider this. In these intergalactic gulfs, cold isn't a side effect. It's the default, the norm. Warmth is the exception. Heat, life, and motion all arise in small, dense pockets. Galaxies, stars, planets. The rest is cold and quiet. But what about the coldest types of stars? We've mentioned white dwarfs and the hypothetical black dwarfs. But there's also a category of star-like objects that were never stars to begin with. Brown dwarfs. Brown dwarfs are often called failed stars. They form from collapsing gas clouds like stars, but they don't have enough mass to ignite sustained fusion. Without fusion, they don't shine like stars do. Instead, they glow dimly in infrared, and only for a while. Some of the coldest known brown dwarfs are just barely above the freezing point of water, between 250 and 300 Kelvin. That's roughly the temperature of a warm spring day on Earth. But in stellar terms, that's freezing. One such object, WISE 1828-650, is a nearby brown dwarf whose temperature may be as low as 250 Kelvin. Another, WISE 0855-0744, as mentioned earlier, may be even colder, potentially cold enough to form water clouds in its atmosphere. These are among the coldest free-floating star-like bodies ever discovered. So what's it like near one of these? From a distance, it would appear almost invisible to the human eye. No bright light, no radiant heat. Just a barely glowing ember hidden in infrared. You could orbit one, land on a nearby moon, and never see its light without a telescope. It's like orbiting a phantom, a star that never quite woke up. Let's zoom out again, not to specific objects, but to consider what cold teaches us about the nature of the universe. Cold slows everything. In physics, temperature is just a measure of particle motion. At high temperatures, particles move fast, collide, create reactions. At low temperatures, motion slows. Structure forms. Order emerges. Consider crystals. On Earth, snowflakes form when water molecules, slowing down in the cold atmosphere, arrange themselves into intricate symmetrical patterns. No two snowflakes are alike, but all share that hexagonal order. This process is guided by the same principles seen across the universe. Cold creates structure. In deep space, the same thing happens with dust grains and molecules. In molecular clouds, atoms settle onto cold dust surfaces and freeze in place, slowly building layers of complexity. Carbon chains, organic compounds, prebiotic molecules, all forming not in fire, but in the chill of deep space. This reveals something profound. Complexity thrives not in heat, but in cold. Life, as we know it, may have had its seeds scattered and preserved in the deep freeze of space, later delivered by comets, asteroids, and meteorites. The famous Murchison meteorite, which fell in Australia in 1969, was found to contain over 70 amino acids, some not found on Earth. These molecules had been frozen in space for billions of years. Cold is not an obstacle to life. In many ways, it's a library, a time capsule. Let's now drift back toward the edge of our solar system, into the Oort cloud. This theoretical shell of icy object is believed to surround the solar system at a distance of up to 100,000 AU, astronomical units. That's over 1,500 times farther than Pluto. Here, sunlight is a memory. Temperatures may be as low as 4 Kelvin. These icy bodies, comets, fragments, frozen relics, are ancient leftovers from the formation of the solar system. Occasionally, one is disturbed by gravitational tides and begins a long, slow fall toward the sun, becoming a comet visible in our skies. But most remain undisturbed for billions of years, unchanged, untouched, cold. And this brings us to a humbling realization. The majority of the solar system is cold. The warm, bright region near the Sun is a tiny sliver. The rest, out past Neptune, beyond the Kuiper belt, through the scattered disk and into the Oort cloud, is silent, vast, and frozen. And beyond that, just stars drifting in cold space, galaxies swimming through colder voids, clusters surrounded by even darker emptiness. We live in a warm oasis, but around us is a sea of quiet cold. Tonight, you've followed this journey from glowing white dwarfs fading into blackness, to brown dwarfs colder than desert nights, to intergalactic voids barely touched by time. Cold is the heartbeat of the cosmos. It's what the universe returns to when things settle, when movement slows, when energy is spent. Not destruction, not chaos, but silence, peace, stillness. And in that stillness, things are preserved, awaiting discovery, waiting for a warm mind like yours to wonder about them. You have already drifted among brown dwarfs, black dwarf embers, and sprawling intergalactic gulfs. Now let's tighten the focus and watch humans, and the universe itself, chase temperatures only a whisper above nothing. It might feel strange that some of the coldest places ever created are inside metal chambers or floating laboratories rather than distant space. Yet that is exactly where the frontier lies. When scientists talk about a millionth or even a billionth of a Kelvin, they are not exaggerating. Those numbers are real, and they expose physics normally hidden behind the blur of thermal motion. Picture the International Space Station, a bright filament arcing across Earth's night. Tucked inside one module is the Cold Atom Lab, a suitcase-sized machine that produces Bose-Einstein condensates in microgravity. On Earth, gravity tugs ultra-cold clouds downward, forcing experiments to last only a fraction of a second before the atoms fall out of range. In orbit, the same cloud can drift, weightless, for several seconds, long enough for lasers and magnetic fields to comb energy from each atom until their collective temperature falls to a few hundred picokelvins. At that point, individual atoms lose their separate identities and merge into a single quantum wave tens of micrometers across, large enough to be photographed. You are seeing matter act like light, coherence writ large, a calm so deep that vibration itself is barely a rumour. That calm is not just a laboratory curiosity. Every atom in your body was once part of a similar ultra-cold cloud nearly 14 billion years ago. After the Big Bang, the universe expanded and cooled so rapidly that hydrogen drifted in a fog only a few kelvins above absolute zero. Those atoms later clumped into galaxies, but for a brief cosmic moment, everything was as serene as the vapor inside the Cold Atom Lab. By recreating those conditions in orbit, scientists are replaying the opening notes of creation and watching how quantum rules sculpt the larger symphony that followed. Cooling ordinary matter is impressive. Cooling antimatter is astonishing. At CERN, the alpha and G-bar collaborations trap antihydrogen atoms, mirror images of hydrogen with positrons circling antiprotons inside magnetic bottles. If an antiparticle touches the wall, it annihilates, so there is no margin for error. Yet researchers have now bathed these trapped atoms in tuned laser pulses until they settle below half a Kelvin. The goal is to let them fall freely and check whether antimatter experiences gravity the same way regular matter does. Only in furious cold can that fall be measured without thermal jitter. Half a Kelvin is still warmer than the Boomerang Nebula, but the conceptual daring is unmatched, probing the symmetry of reality itself through a discipline of near absolute stillness. The cosmos supplies its own natural laboratories. One of the strangest is the so-called CMB cold spot, a patch of sky in the southern hemisphere where the microwave background dips roughly 150 microkelvin below average. The leading explanation is a gargantuan supervoid, an underdense region hundreds of millions of light-years across, through which photons lose a touch of energy while climbing out of a slightly deeper gravitational well. Whatever the cause, that deficit marks the single coldest large-scale pixel on the observable sky map, a footprint of structure grander than any galaxy cluster. Standing there, if there existed as a local place, you would not notice a chill on your skin. The drop is tiny. Yet embedded in those microkelvins is evidence about how inflation sculpted the early universe, how dark energy tugs at empty space, and why subtle wrinkles in the primordial fireball still echo today. Another line of evidence for hidden frigidity arrived in 2018, when the EDGES radio array detected an unexpectedly deep 21-centimeter absorption signal from atomic hydrogen about 180 million years after the Big Bang. The dip implied gas colder than previously thought, too cold, unless something outside the standard model siphoned heat away. One hypothesis suggested a wisp of dark matter that interacts feebly with baryons, drawing off energy and leaving hydrogen at perhaps 3 kelvins when theory predicted. The observation is still debated, but it demonstrates how temperature measurements can expose invisible physics. Chill the gas a little beyond expectation, and you may be forced to rewrite cosmology. Cold does not belong only to intergalactic voids, it also hides inside giant planets. Dive deep under Jupiter's luminous cloud tops, and you reach a zone where pressures crush hydrogen into a metallic form, while helium condenses and rains inward like shimmering droplets. Those droplets fall through warmer layers toward the core, releasing gravitational energy that warms the planet and, paradoxically, creates a local region slower than the layers above and below. Beneath Saturn's pastel bands, the process is gentler but more extensive. Helium snow may accumulate into slushy shells tens of thousands of kilometers thick. In other words, parts of a gas giant's interior mimic the insulation of an ultra-cold laboratory, separating phases so alien that we have no direct analogue on Earth. Saturn's rings showcase a different flavor of cosmic refrigeration. Each ring particle, mostly water ice pebbles laced with dust, orbits in near-perfect vacuum, illuminated but never baked because Saturn lies 10 times farther from the Sun than Earth. Daytime ring temperatures hover around 70 kelvins, but on the night side, shielded from sunlight and reflecting little infrared from the planet, surfaces can plunge below 30 kelvins. The result is ice so clean and bright, it reflects almost all incoming light, giving the rings their luminous sheen. These grains endure minimal chemical change. They are time capsules from the birth of the solar system, swirling freezers preserving whatever molecules condensed out of the primordial nebula. Then there are cryovolcanic worlds, places where cold controls the kind of heat that can escape. On Neptune's moon, Triton, plumes of nitrogen gas erupt through dark vents when meager sunlight warms a translucent ice layer just enough to trigger sublimation. On Enceladus, fractures near the South Pole release fountains of salty vapor that flash freeze into snow, feeding Saturn's E-ring. The internal oceans powering these geysers are warm by comparison, but the vacuum above them is frigid, capturing the spray in a glittering halo. Even volcanoes can be instruments of cold if the surrounding air is hard vacuum and the temperature difference is vast. Every path you follow eventually meets a curtain drawn by the third law of thermodynamics. Absolute zero cannot be reached through a finite sequence of steps. There is always a final jitter, a stubborn quantum zero point that refuses to vanish. Yet the pursuit itself is revelatory. Lower the temperature and hidden orders emerge: superconductivity, superfluidity, magnetism trapped in perfect lattices. Within neutron stars, the nuclear pasta at the crust may pair into superfluid sheets and filaments, letting the star's crust glitch as angular momentum transfers catastrophically from the liquid interior. Within laboratories, electrons deprived of thermal agitation lock into conduction channels with zero resistance, lighting the path to quantum computers and precision sensors. In both cases, cold is the clarifying lens that shows structure otherwise blurred. Step back and look at the grand ledger. Helium snow drifting through gas giant skies, antihydrogen shimmering in magnetic cages, microwaves cooled by cosmic expansion, hydrogen chilled by dark matter whispers, condensates blooming in microgravity. All different stories, one common theme. Whenever motion slackens, nature's finer brushstrokes appear. Cold is not emptiness, it is revelation. It makes the invisible visible, slows the frantic, and preserves the fragile. So as you contemplate these scattered laboratories, from a vacuum chamber orbiting 400 kilometers overhead to a shadowed swath of cosmic background light billions of light years away, remember that temperature is not just a reading on a scale, it is a narrative of energy, vibration, and time. Where that narrative nearly pauses, you can survey the deep grammar of reality. And the universe, with patient generosity, keeps furnishing places where the pause grows long enough for us to listen. By now, you've seen that cold is not just the background of the universe, it's the framework. It's what the cosmos settles into when energy fades, when collisions stop, and when light loses its voice. But in this part of our journey, let's go deeper. Not just into what is cold, but into what will become cold. We'll explore the future, distant epochs of frozen silence, where stars die, light stretches beyond visibility, and the universe becomes a gallery of motionless remnants. Let's begin at the end of time, not poetically, but thermodynamically. The universe, as far as we know, will not end in fire, but in a slow and final freeze. This is the concept of heat death, a misleading name for a very cold reality. As space expands, galaxies drift further apart. Over trillions of years, the stars within them will exhaust their nuclear fuel. The bright ones die in explosions. The medium ones fade into white dwarfs, then black dwarfs. The giants collapse into neutron stars or black holes. Eventually, no new stars will form. The interstellar gas that fuels star birth will be used up, and the night sky, across all worlds, will grow darker. This will be the degenerate era, a time when the universe is lit only by the faint heat of stellar remnants. Over time, even these dim corpses will cool. Black dwarfs will approach temperatures indistinguishable from the void. Imagine that, billions upon billions of Earth-sized spheres made of carbon and oxygen, completely black, completely silent, slowly orbiting in empty space. They are the embers of a fire that once burned across the universe. But in the cold, they no longer shine. Even black holes, the last devourers of matter, won't last forever. According to Stephen Hawking's theory, black holes slowly emit radiation, Hawking radiation, and shrink over time. For large black holes, this process is imperceptibly slow. But given enough time, So much time we don't even have a word for it. They will evaporate. The universe will lose its last sources of heat, and entropy will finally approach its maximum. At that point, all usable energy is gone. No motion, no fusion, no friction, just particles scattered across expanding space. The temperature will dip toward absolute zero, not reaching it, never reaching it, but so close that even the difference becomes meaningless. The cold era will have begun. Now, while that paints a quiet and lonely picture, let's return to the present, to what cold does in the now. There are entire environments, even within our own Milky Way, where cold dictates structure, life cycles, and possibility. Take interstellar ices. In dark molecular clouds, molecules like water, carbon dioxide, ammonia, and methane freeze onto dust grains, forming icy mantles. These grains serve as platforms for chemistry that cannot occur in the gas phase. With enough time and the occasional cosmic ray trigger, they produce complex organic molecules, some of which are ejected into space when nearby stars ignite and send shockwaves through the cloud. These molecules have been detected around forming stars, and even in the cold outer reaches of planetary systems. Some make their way into comets, dirty snowballs that carry this interstellar chemistry into the inner regions of solar systems. When comets pass near their host stars, they heat up, release gases, and create the glowing comas and tails we see from Earth. But the story behind that glow started billions of years earlier, in the silence of a frozen cloud light years away. Cold preserves, but it also transports. And this principle continues on planetary moons, places like Europa and Ganymede. Beneath their icy crusts lie oceans, kept liquid by internal heat but sealed off from the universe by kilometers of solid water ice. The surface of Europa, for example, hovers around 100 Kelvin. The vacuum of space ensures that once water freezes, it stays frozen indefinitely unless something stirs it from within. That means everything on that surface, every crack, every ridge, could remain unchanged for millions of years. A frozen history book, untouched by wind or rain. But those frozen surfaces may hide life. Scientists believe Europa and Enceladus both have subsurface oceans rich in salts and organic molecules. If microbial life exists in those seas, it may be among the oldest and most resilient forms of life in the galaxy. Its shelter is the cold. Without the ice, the ocean would evaporate into space. It is only in this deep freeze that warmth survives. That's one of the strangest truths of planetary science. To find liquid water, we look for the coldest places. Not deserts, not sun-scorched worlds, but icy moons with hidden warmth beneath. Cold on the outside, warm within. Now imagine the future of space exploration. The ships that may one day travel between stars. To conserve energy, they too may need to embrace cold. Cryogenic sleep, once a science fiction trope, is now being studied seriously. Not freezing people solid, but cooling the body to near hibernation states. Slowing metabolism, stretching time. Just like atoms in the Boomerang Nebula, future travelers may learn to rest in a state of suspended animation, held just above the thermal bottom. We've already learned how to freeze embryos, tissues, and even entire organisms like tardigrades. The next steps could involve storing complex systems in ultra-cold states for years or decades, awakening them only when destinations are near. Cold becomes a passage, not an end. Let's shift one more time to a forgotten corner of our galaxy, the galactic halo. This spherical region surrounds the Milky Way's spiral arms and contains ancient stars, globular clusters, and a mysterious component: dark matter. The stars in the halo are some of the oldest in the universe. They orbit on wild, elliptical paths, untethered from the galactic plane. Temperatures here are extreme, both in heat and cold. Gas clouds in the halo can plunge to a few Kelvin, shielded from stellar radiation. The stars themselves are often dim red dwarfs, burning slowly, taking trillions of years to exhaust their hydrogen. If you lived near one, you'd be in the coldest, loneliest outskirts of the galaxy, barely warmed by a fading ember. But again, cold doesn't mean unimportant. These ancient stars act as fossils of galactic evolution. Their chemistry holds clues to how the Milky Way formed. Their motions map the gravitational web of unseen matter, and the gas clouds, though faint, may one day collapse to form new generations of stars, restarting the cycle in the cold. You see, the universe doesn't fear the cold, it uses it. Cold is a sculptor. It shapes rings and orbits, preserves molecules, slows reactions, and reveals the subtle geometry of quantum states. It turns vapor into crystal, light into structure, matter into order. Tonight, you've followed the trail of that order, from icy moons to future starships, from frozen clouds to final fates. You've watched stars fade, molecules hibernate, and the cosmos itself coast towards silence. And maybe, as you rest, you'll feel it too, not as absence, but as clarity. Because the coldest places in the universe are not dead. They are waiting, holding still, letting time move at the pace of thought. In the darkness between stars, where temperatures fall to just a few degrees above absolute zero, the universe is conducting experiments. Slow, silent, but astonishingly complex. You might imagine these frozen environments as empty, but in truth, they are alive with chemistry, just not the kind we're used to. In this part, we'll look at how cold isn't just an absence of energy, but a condition that enables unique forms of interaction, creation, and perhaps even the very beginnings of life itself. Let's return to the coldest natural regions, dark molecular clouds. These immense structures, some hundreds of light years across, are among the coldest places in the galaxy, with internal temperatures hovering around 10 Kelvin. Inside, light can't penetrate, and temperatures are so low that nearly all gases freeze onto dust grains, forming icy coatings. You might think chemical reactions stop here, but the opposite is true. These dust grains act like laboratories, allowing atoms and simple molecules to land, freeze, and react over time. And because the temperatures are so low, nothing is destroyed by heat. Molecules can accumulate layer by layer. This is how some of the building blocks of life begin: methanol, formaldehyde, ethanol, formic acid. Many of these have been detected in interstellar clouds. Even more complex compounds like amino acids and nucleobase precursors have been discovered in meteorites, indicating they likely formed in space long before landing on Earth. And here's the astonishing part: these structures require cold. Heat would have torn them apart. At near zero temperatures, reactions occur not through fast collisions, but through quantum tunneling, a phenomenon where particles pass through energy barriers they shouldn't be able to cross. It's like watching a marble roll uphill and vanish through a wall. At high temperatures, this is rare, but in the cold, it becomes dominant. The universe, in its deep freeze, finds a back door into complexity. And this isn't just theoretical. Observations from ALMA, the Atacama Large Millimeter, Sub-Millimeter Array, have confirmed the presence of prebiotic molecules in forming star systems. embedded in icy disks around young stars. These aren't random chemicals, they're potential ingredients for life, caught mid-transit, frozen in orbit. Now consider the journey of a comet, formed in the early solar system and exiled to the Oort cloud. It spends billions of years frozen, untouched, unchanged. Then, a small gravitational nudge sends it inward toward the sun. As it warms, its ices vaporize, releasing gases and dust that had been trapped for eons. That's not just a tale, it's a chemical time capsule unsealing itself. Some scientists speculate that Earth's water, and possibly its first organic molecules, were delivered by impacts from these ancient travelers. Without cold, none of this would be preserved, and without preservation, there's no inheritance. Cold is a memory keeper, but it's not just molecules that benefit from low temperatures. On a deeper level, temperature shapes how atoms interact with light, with one another, and even with space itself. Atoms at room temperature bounce and collide constantly, but as they cool, they slow, their movements becoming more synchronized. Eventually, under the right conditions, they can enter a state of matter known as a Bose-Einstein condensate. Here, individual atoms lose their identity. They behave as one quantum object with a shared wave function. This was first achieved in a lab in 1995 using rubidium atoms cooled to 170 nanokelvin, less than a billionth of a degree above absolute zero. The atoms were essentially frozen in time. Why does this matter? Because in this state, matter behaves in ways we've never seen before. It can flow without resistance. It can climb walls. It can be interfered with like light. And these behaviors offer us a glimpse of how the universe might behave under extreme conditions, like inside neutron stars or just after the Big Bang. We don't find Bose-Einstein condensates naturally in space, at least not yet, but ultra-cold hydrogen clouds or dark matter interactions might mimic similar properties. Some theories even suggest dark matter itself may form condensate-like structures on galactic scales, held together not by heat, but by coherence. Cold, it seems, isn't just a temperature. It's a state of information. Now zoom back out. Picture a galaxy. Bright, spinning, filled with billions of stars. But the bright part is just the surface. Most of the galaxy's mass lies in its cold outskirts, in vast halos of invisible matter, and in hidden reserves of cold gas. This gas is a kind of galactic future. It hasn't yet formed stars, but it might. It waits. Astronomers use radio telescopes to detect cold hydrogen gas through its unique 21 centimeter line, a faint whisper that lets us map the invisible. It's how we know galaxies extend far beyond their visible edges. It's how we trace spiral arms, voids, and filaments that hold the universe together. Even the cosmic web, the largest structure in existence, is defined in part by where cold gas flows. Galaxies don't just sit in isolation. They grow at the intersections of cold streams, and those streams feed them, like rivers feeding trees. Let's pause there. Let that image settle. Cold as a river, slow, invisible, persistent. Not a threat, a source. In the farthest reaches of space, in places we may never visit, cold allows things to persist. Not decay, not erupt, but simply endure. A planet in permanent shadow. A star frozen mid-collapse. A nebula holding its breath. Cold is the custodian of quiet things. And that may be why the coldest places in the universe matter most. Not because they are dramatic, but because they are stable. In a universe born in fire, cold gives us time. Time for molecules to build, time for stars to form, time for life to emerge. When we think of stars, we think of blazing heat. Our sun, for instance, burns at over 5,500 degrees Celsius on its surface. But not all stars are created equal. Some fail to ignite entirely. Others burn low and slow for trillions of years. And some collapse into silent, frozen embers. In this part, we'll explore stars that are defined not by their heat, but by their astonishing cold. Let's begin with the smallest stars that do manage to ignite, red dwarfs. These stars are the most common in the universe, making up nearly 75% of all stars. But they're faint, so faint you can't see a single one with the naked eye, despite their abundance. Red dwarfs burn hydrogen very slowly, with surface temperatures as low as 2,500 degrees Celsius, much cooler than our sun. Some are so dim they're barely distinguishable from planets. Their low temperature means they live incredibly long lives, up to 10 trillion years or more. And here's something remarkable. The universe isn't old enough for any red dwarf to have died yet. Every red dwarf ever formed is still shining today. But we can go colder still. Enter the brown dwarf. These are sometimes called failed stars, and the name is fitting. Brown dwarfs form like stars, from collapsing clouds of gas, but they never accumulate enough mass to ignite hydrogen fusion in their cores. Instead, they glow faintly from the heat of their contraction and initial formation, slowly cooling over time. A brown dwarf might begin with a surface temperature of 1,000 pounds and 2,000 Kelvin, but as it ages, it cools indefinitely. Eventually, its temperature can fall below that of a human body. In fact, the coldest brown dwarf ever discovered, WISE 0855 0714, is only about 250 Kelvin or 23 degrees Celsius. That's colder than the freezing point of water. This object is just 7 light years away, yet it emits almost no light. It's invisible in optical wavelengths. We detect it only by its faint infrared signature. In many ways, it blurs the line between star and planet. It has no solid surface, but its atmosphere likely contains water clouds and even rain. So imagine that, a nearly frozen, Jupiter-sized object drifting silently through space, colder than an Antarctic winter, yet once part of a star's evolutionary story. And then there are the stellar corpses, white dwarfs and neutron stars. When stars like our sun exhaust their fuel, they shed their outer layers and leave behind a dense core, a white dwarf. These remnants are no longer fusing atoms, they shine only because of residual heat, and over billions of years that heat fades. A white dwarf starts hot, up to 100,000 Kelvin, but cools steadily over time. The oldest, coldest white dwarfs are around 4,000 Kelvin, cooler than some red dwarfs, but they're still hot compared to their ultimate fate. Given enough time, trillions of years, a white dwarf will cool to the temperature of the cosmic microwave background, just 2.7 Kelvin. At that point, it becomes a black dwarf, a hypothetical object, because the universe isn't old enough for any to exist yet. Black dwarfs would be completely cold and completely dark. They'd emit no visible light. They'd be invisible in every practical sense. But they would still exist. Ultra-dense spheres of carbon and oxygen crystallized into silence. It's a haunting image. Stars that once burned with light, now cold, black, and invisible. Not destroyed, just faded. Let's now visit an even stranger idea: rogue planets. These are planets that were once part of a solar system, but were flung into interstellar space, ejected by gravitational interactions, collisions, or the death of their parent star. Once detached from their sun, these worlds become wanderers, drifting alone in the darkness. With no sun to warm them, they grow cold, very cold. Surface temperatures may fall below 50 Kelvin. Their atmospheres, if they have any, can freeze. Yet, surprisingly, they may not be entirely dead. Some rogue planets might retain internal heat, especially if they are massive and geologically active. If they have thick insulating layers, subsurface oceans could exist beneath icy shells, kept liquid by radioactive decay or tidal heating from past encounters. Even without a sun, such a planet could harbour life in a hidden ocean. We know of at least a dozen candidates for rogue planets, and estimates suggest there may be more of them than stars. The cold darkness between stars may be full of unseen, frozen worlds. Imagine that for a moment. Entire planets, lost in space, with no sunrise, no orbit, no sky. Just a slow, unending drift through night. Silent, frozen, eternal. Let's return to stars now, but shift our focus to the cold remnants of supernovae, neutron stars. These are among the densest objects in the universe, formed when a massive star explodes and its core collapses. A neutron star can pack more mass than our Sun into a sphere just 20 kilometers wide. The surface temperature after formation is around 1,000,000 Kelvin, but it cools rapidly. In the deepest time frames, neutron stars will also cool to near absolute zero. Their outer crust may become frozen, rigid, like iron ice. Some theories suggest they could form nuclear crystals, solid structures held together not by molecular forces, but by neutron pressure. But just like white dwarfs, they cool over timescales longer than the universe has existed. In theory, all neutron stars will eventually become inert, cold objects, a type of ultra-dense frozen ghost star. And then, finally, we come to the coldest stellar concept of all: dead black holes. Black holes themselves aren't technically cold or hot in the traditional sense, since they don't have a surface. But they do radiate something called Hawking radiation, a quantum effect that allows them to slowly evaporate over time. For stellar mass black holes, this process is unimaginably slow, longer than the current age of the universe by over 10⁻60 years. But when they do finally radiate away all their energy, they will vanish entirely, leaving behind a kind of quantum residue, a state colder and quieter than we can currently define. In the far, far future, after all stars have died, all white dwarfs and neutron stars have cooled, all black holes have evaporated, the universe may be left in a state of near total darkness and cold. A quiet sea of subatomic particles drifting in 3 Kelvin shadows. This is the degenerate era, a time dominated not by stars or galaxies, but by frozen remnants. The night will last forever. There will be no new light, only the echo of what once was. And yet, this long cosmic winter is part of the story, a chapter that must follow the fiery brilliance of the beginning. Cold is not the end, it's the equilibrium. The silence after the song. So far, we've explored frigid moons, frozen stars, icy planets, and dying embers of suns. But there's a colder realm still, one that exists not on surfaces or inside atmospheres, but in the vast gulfs between. This part of our journey takes us into the void itself, into the emptiest places in the universe, where cold reaches its ultimate expression. Let's start by talking about what temperature really means. Temperature is a measure of the motion of particles. The more they move, vibrate, bounce, rotate, the hotter a substance is. When movement slows, temperature drops. And when it stops almost entirely, you get something astonishing. Temperatures approaching absolute zero. Absolute zero is the coldest possible temperature. It sits at 0 Kelvin, or 273.15 degrees Celsius. At this point, all classical motion ceases. Atoms stop moving, molecules freeze into complete stillness. This is the absolute limit of cold. Nothing in the universe has been measured at exactly 0 Kelvin, but some places get very close. The coldest naturally occurring environment in the universe isn't on a planet or moon. It's in the space between galaxy clusters, the vast, dark, intergalactic voids. These regions are so empty they contain only a few hydrogen atoms per cubic meter, and those atoms have almost no energy. These voids have a temperature just slightly above the temperature of the cosmic microwave background. 2.7 Kelvin. That's only 2.7 degrees above absolute zero. The only reason they're not colder is because of the lingering glow from the Big Bang, still warming the universe ever so faintly, even 13.8 billion years later. That faint glow, the CMB, is the afterlight of creation. It fills all of space, evenly and softly. If it weren't there, the voids would be even colder, possibly just fractions of a Kelvin above zero. These are the coldest places known to naturally exist. Imagine drifting through that emptiness. No light, no planets, no dust. Just an ocean of near nothingness. Not even gravity is strong here. Space itself is nearly flat. It's not just cold, it's inert. Let's now zoom in to one of the strangest and most isolated places in our own galaxy, the Boötes Void. Discovered in the 1980s, the Boötes Void is a massive region of space, about 330 million light-years across, with very few galaxies. For a long time, astronomers were puzzled by its emptiness. How could such a massive volume contain so little? The Boötes Void has sometimes been nicknamed the Great Nothing. It's not entirely empty. There are galaxies scattered inside, but they're far apart, separated by unimaginable distances. The temperature inside this void is believed to be among the coldest in the known universe, hovering just above the cosmic background. It's not just empty, it's lonely. If you were on a planet inside the Boötes Void, the night sky would be nearly starless. In every direction, you'd see darkness. Yet this isn't the coldest engineered place. To find that, we turn to Earth, specifically to laboratories that have cooled matter closer to absolute zero than anywhere else in the cosmos. In 1995, scientists at the University of Colorado created the first Bose-Einstein condensate, a state of matter that forms at temperatures just billionths of a degree above absolute zero. In this state, atoms lose their individual identity and behave as one quantum entity, a kind of atomic superfluid, perfectly still and coherent. This was the coldest temperature ever achieved on Earth. Then, in 2018, NASA launched the Cold Atom Lab aboard the International Space Station. This device allows scientists to cool atoms to just a few nanokelvin above absolute zero, in a weightless environment, free from Earth's gravity. This lets the atoms stay cold for longer and behave in even more exotic ways. So yes, in a strange twist, the coldest known temperatures in the universe exist not in deep space, but in human-made laboratories in low Earth orbit. But natural cosmic cold still holds its own surprises. Let's visit a particular object called PSR J21443933, a pulsar located about 400 light-years away. It's a neutron star, and what makes it unique is its temperature, estimated at below 42,000 Kelvin. That might sound hot, but for a neutron star, it's unusually cold. Most are still millions of degrees. Even more impressive is XMM J1732033444518, a compact object located in the supernova remnant G353.60.7. This one has an upper temperature limit estimated to be as low as 100,000 Kelvin, still much hotter than space, but frigid by neutron star standards. These cold remnants are windows into the future. They show us what the universe will eventually become: quiet, dark, and inert. Another candidate for cosmic cold is dark matter. We don't yet know what dark matter is made of. It doesn't emit or absorb light, and it doesn't interact with ordinary matter very much. But one possibility is that dark matter exists at extremely low temperatures, close to absolute zero. If it's made of weakly interacting massive particles, WIMPs, it might behave like a cold gas, drifting silently through space. That's why it's sometimes called cold dark matter, not because we've measured its temperature, but because it moves slowly, with very little kinetic energy. It might be the most abundant cold substance in the cosmos, forming the hidden skeleton of galaxies and shaping the structure of the universe, invisibly. So we now see that cold is not always absence. It can be form, a state, an invisible architecture. And this brings us to the grandest scale of cold, the ultimate fate of everything. In cosmology, the heat death of the universe isn't about fire, it's about temperature reaching an equilibrium. Over trillions and quadrillions of years, energy will spread out evenly. Stars will die, black holes will evaporate, galaxies will dissolve, and all that will remain is a vast, cold sea of particles. The temperature, just a fraction above absolute zero. The structure, homogeneous, no gradients, no usable energy, just silence and cold. This is called thermodynamic equilibrium, and it may be our universe's final state, not with a bang, but with a shiver. And yet, there is beauty here, because every cold object tells a story. It's not just the absence of heat, it's the evidence of what came before. A frozen moon tells us about solar formation. A black dwarf tells us about stellar aging. A void tells us about the fabric of space itself. Cold carries memory. The colder the object, the older the tale. And so as we float in this cosmic stillness, we come to appreciate a strange truth. The universe's quietest places are also its most profound. They whisper about time. They echo with the birth and death of stars. They are more than darkness. They are deep, silent maps of everything that ever was. By now, we've travelled from icy moons and cryogenic planets to the frozen silence between galaxies. But there's more to cold than just temperature. It also affects how the universe glows, how it moves, and even how it thinks. In this part of our journey, we'll look at some of the most intriguing consequences of cosmic cold, how it alters light, bends time, and reveals the universe's most secret rhythms. Let's begin with something surprising: cold light. You might think of light as hot, especially from sources like stars or fire, but the light that dominates the universe, the cosmic microwave background, or CMB, is cold. Very cold. This faint afterglow of the Big Bang permeates all of space, arriving at Earth as microwaves with a temperature of just 2.725 Kelvin. Though it's light, it's as cold as any place we've visited. This radiation was once blindingly hot, thousands of degrees Kelvin. But it's been stretched and cooled over billions of years by the expansion of space. As the universe expands, the wavelength of light stretches. This is called cosmological redshift. Photons lose energy, becoming longer and colder. What began as high-energy visible or ultraviolet light becomes cold microwave radiation, and one day it will be stretched even further, becoming radio waves so faint they can barely be detected. This is the fate of light in a cold universe. It slows, fades, and stretches into silence. Now imagine trying to observe a distant galaxy. The light from it has traveled for billions of years, through expanding space, losing energy all the while. It arrives not in a blaze, but in a whisper, a faint glimmer near the edge of detection. Some of the most distant galaxies we've discovered are not bright to us. They're dim red smudges seen only in infrared. The James Webb Space Telescope, for instance, is optimized for this kind of work, not because the galaxies are faint, but because they've been cooled and redshifted by the universe itself. The colder the space the light travels through, the less energy it retains. Eventually, as the expansion continues, photons will have such long wavelengths that they'll carry almost no usable energy at all. And this leads us to the idea of a dark future. As stars die and galaxies recede beyond our horizon, the universe will grow colder and darker. Fewer stars will be born. Fusion will cease. Black holes will evaporate over trillions of years through Hawking radiation, a process so slow it's almost unimaginable. But it, too, cools over time. The evaporation of a black hole releases particles in a thermal spectrum, hot at first, but gradually decreasing in temperature as the black hole shrinks. Eventually, when the black hole is tiny, it will evaporate in a final burst of heat and radiation. After that, the matter it consumed will no longer be gravitationally bound. It will simply drift, growing colder and colder. The ashes of the universe will not be fiery, they'll be freezing. Even the particles themselves, protons, neutrons, and electrons, may decay. We don't know for sure. If they do, the universe will one day contain only radiation and neutrinos, both extremely cold, extremely low energy. It's not just the environment that becomes cold, it's the very structure of time. In thermodynamics, entropy is a measure of disorder. As systems cool, entropy increases, not because things are getting more random, but because energy is spreading out. In the far future, everything will be at the same temperature, a uniform cosmic bath just above absolute zero. And with no temperature differences, there will be no motion, no work, no information transfer, no time in any meaningful way. A timeless universe, still, silent, and cold. This concept is called the heat death of the universe. But that name is misleading. It's really a cold death, a universe so uniform and still, it can no longer change. But what about now? Is the universe cold today? Yes, mostly. The average temperature of space, thanks to the CMB, is 2.7 Kelvin. Most of the volume of the universe is made up of empty space. Planets, stars, and galaxies are the exception, not the rule. When we think of space, we often imagine stars and glowing nebulae, but the reality is much more austere. If you could pause time and float in the emptiness between galaxy clusters, you would experience the dominant condition of the cosmos: pure cold. There are places so empty they contain no atoms at all, just radiation, not even photons with enough energy to interact with matter. These are cosmic voids, and they are vast. often spanning hundreds of millions of light years. If you entered one of these voids, you'd see almost nothing. No stars, no dust, just blackness. The nearest galaxy could be millions of light years away. Your body would radiate more energy than the space around you. Now consider this. Even atoms, the building blocks of matter, have temperature. The electrons around a nucleus vibrate in tiny orbits. But if you cool those atoms to near absolute zero, their quantum behavior dominates. This is what happens in Bose-Einstein condensates. Collections of atoms that merge into a single quantum state. These condensates are often colder than anything found naturally in space. They exhibit bizarre behaviors like superfluidity, flowing without resistance, and perfect coherence. In these ultra-cold states, matter reveals a strange truth. The colder things get, the more quantum they become. The classical world of objects and motion gives way to a universe of probabilities, waves, and entanglement. Cold isn't just a state, it's a doorway to quantum reality, and perhaps even to information. Some scientists speculate that at ultra-low temperatures, it may be possible to preserve quantum information in ways that are otherwise impossible. Think of it like a cosmic deep freeze, not just for atoms, but for thought, computation, and memory. This has implications for long-term communication and storage across time. Could we preserve consciousness? Could information be frozen into the fabric of space? It's speculative, but it's also deeply poetic. Now let's return to a cosmic scale and ask, what's the coldest object in space? One candidate is the Boomerang Nebula, which we visited earlier. Its temperature of 1 Kelvin makes it colder than the cosmic microwave background, thanks to its rapid gas expansion. But this may not last. Eventually, it will warm back up, rejoining the rest of the universe at 2.7 Kelvin. Other regions, like the intergalactic medium or the outer edges of dark matter halos, may compete for the coldest natural environment. But none are as precisely measured as the Boomerang. And yet, the coldest known environments of all are in laboratories. That's right, humans, tiny blips on a cosmic scale, have created temperatures colder than anything nature has managed on its own. With lasers, magnetic traps, and careful engineering, we've chilled matter to just billionths of a Kelvin. In those states, time itself seems to slow. Motion ceases. Atoms lose their individuality. The world becomes transparent to quantum laws. It's a strange kind of triumph. While the stars rage in heat and galaxies burn with energy, we've created pockets of stillness, tiny windows into the ultimate cold. And through them, we glimpse not just the future of the universe, but its hidden structure, because cold isn't the enemy of life or motion. It's the canvas on which energy paints. It's the silence that gives music meaning. It's the background hum against which all creation is heard. And one day, as the stars go out and the galaxies fade, all that will remain is that silence, that endless cold. But it won't be empty. It will carry everything the universe has ever done, every burst of light, every echo of time, every memory frozen in the stillness.